Hello? We're here. Awesome. All right. My name is Ilya Ganelin. I'm part of the Vault 8 team at Capital One. Today, I'm going to be talking about my experience with Spark over the past 8 to 9 months and lessons that I learned while building out a recommendation engine on top of our transactional data. So this is not working. We'll use the keyboard. It's lessons from Spark, or how I learned to stop worrying and love the shuffle. What we were trying to do was to take an enormous amount of transactional data that we have from our credit card customers. We had on the order of 60 million customers, and in the MLlib collaborative filtering terms, 10 million products, which was about 2.5 terabytes of data. The collaborative filter works in a two-stage process. In the first, you train your model to basically be able to predict similarity between users. And in the second stage, you run a predictive step, which actually assigns a score to a particular user for a given product. And the overall amount of math that we had to do was 12 petaflops, which is a substantial amount of computation. And we were doing a few things that were a little crazy. First, because one doesn't usually generate all possible recommendations. Normally, you only care about a small subset. In our case, we specifically wanted to see if we could capture the long tail, specifically those recommendations which wouldn't be common, right? We don't want to just tell you to go to Macy's. We want to really be able to capture that small neighborhood shop that you and only a few people really close to you are interested in. The other thing that we did that was a little nuts was that we were doing all this compute on only 6 nodes in a shared environment, right, where people were actually regularly running production jobs. Which meant that we couldn't just hog the cluster and use as much of memory as we would want. And Spark does love its memory. And the other thing was that we were initially working with Spark 1.0, then 1.1 and 1.2, but far from sort of the cutting edge, which meant that a lot of the improvements to stability and performance weren't present. With this said, this meant that to actually get things to work, I needed to really decompose everything that was going on under the hood, understand it, and to be able to configure Spark properly to actually get it to run. This talk is intended to basically share that knowledge so that regular folks just trying to build stable Spark apps can understand how Spark internals really drive design and what you need to configure in order to get your apps to run to completion and to do so quickly and efficiently. I'm going to initially go over some background. I'm going to talk about partitioning and how that impacts performance. Partitioning is basically how data is broken up on disk. I'm going to talk about caching, which I'm sure you all know and love, and how Spark gets its tremendous improvements in terms of performance. I'll talk about serialization, which becomes relevant because moving data around is expensive. And I'm going to talk about the shuffle, which happens a lot and is simultaneously a source of a lot of problems. And I'll conclude with some sort of summary lessons that detail how all these things tie together and what you can do in the day-to-day to make your life easier. Partitions are how data is split up on disk. This is relevant because when Spark is operating, I'm sure many of you know, Spark defines tasks. Tasks, in turn, assign work to executors in stages. Each stage will operate on a partition at a time. What this means is that, first of all, if you have more executors available than there are stages to process, everything's fine. And you'll always, wrong way. If you have more executors than stages to process, you may be underutilizing your cluster, because if your data is sharded more efficiently, then you can ensure that everything is spinning at full capacity. Secondly, the individual size of a single partition comes into play. Because if you imagine that you have a very large data set, but it's only broken up into a few chunks, any one of those chunks might be quite substantial. What this means is that when it comes time to actually operate on those chunks, you'll need to have a huge chunk of memory available to you to actually process things. And what this means is that if your settings are misconfigured, or as I'll talk about later, you actually have less memory available to you than you think you do, things will break. And the next thing, caching is what allows you to really speed up execution. And basically, instead of writing to disk between subsequent steps in your pipeline, you can cache repeatedly used RDDs in memory, which gives you a dramatic speed improvement, right? Memory is way faster than disk. And this comes into play particularly for machine learning applications. And as we all know, this was the genesis for Spark. And the last thing is serialization. Serialization is basically how data is moved around on the Spark cluster. You have to efficiently encode it and then transport it with some sort of messaging system. Spark uses Akka, and I'll mention it briefly later. But the reason I mention it here is because the default serialization scheme is Java, the built-in serializer in Java. But there's also the alternative implementation available, which is to use cryo-serialization. And when you do that, you can dramatically increase both the speed of serialization, and it uses a lot less memory to move data back and forth. And that proves very useful when you're trying to build things that don't break. So next, I'm going to talk about the shuffle. And sadly, I do not have time to bust out my dance moves. So we can wait for the after party for that. What I'm really talking about is this mechanism that Spark has to organize data when you're performing certain operations, specifically things like joins, reduce by key, or group by key, when you need to aggregate all the values associated with a particular key in a single place so that you can operate on them. Data is split up across all the nodes in your cluster, right? And moving it around involves network, it involves disk. Basically, a whole lot of stuff ends up happening. It's a complex process. And in general, this is almost always where stuff breaks. This involves serialization, as I've already mentioned. It involves Akka, which is the messaging service. And configuring Akka and understanding the parameters involved there also becomes relevant when you're trying to get things to not throw exceptions. There's memory overhead involved. Essentially, to organize how the shuffle happens, Spark will create tables in memory, and when these tables grow too large, in more recent versions of Spark, this will be safely written to disk, so it won't just throw out of memory errors. But this is still expensive, and not to mention, if you are shuffling a lot of files, particularly a lot of small files, you're going to incur significant garbage collection overhead, which is, again, going to slow things down. So really, the message here is that shuffle is both an expensive operation and it is frequently where things break. So with that, let's move on to talking about some sort of summary lessons. The first is that Spark is, at times, very difficult to work with. The biggest problem here is that Spark works great when you have tons of memory available to you and you're not really running into any resource bounds. When you don't have a lot of memory available to you and you're trying to process a whole bunch of data, things fall apart. Part of the reason for this is that there's a lot under the hood, particularly with how memory is broken up, that isn't immediately visible. When you create your Spark context, you'll typically specify how much memory you want each executor to have, but you're also may or may not be specifying something called the memory fraction, which is defining how memory is broken up between shuffle operations, between cached RDDs, and also there's also off-heap memory, which is used for other operations. There's also metadata that accumulates on the driver, which is sort of the orchestrating entity that is handling everything that's going on in your cluster, and data from shuffles and from the scheduler builds up on the driver node. And what I discovered was basically when it came time to actually crunch all this data with not a lot of compute, I got it to run stably, but it still had to run for a long time. And in short, it was the equivalent of a memory leak, right? Like things wouldn't really clean up properly. So again, memory usage that isn't immediately obvious just from documentation or from how you expect Spark to be playing. Finally, there's also this idea that for Scala and Java types versus sort of basic types, there's actually significant overhead in the data structure of, say, a string. The header and wrapper for a string can make it so that a single string, which you'd expect to be on the order of a few bytes, can be as big as 60 bytes. And so you can understand if you think you have really a 1 gig table and you actually have a 6 gig table, things might fall apart if you're only allocating a few gigabytes of memory. The other thing that makes things really hard is that debugging is an immense challenge. We've moved sort of in the right direction in the community. There's a lot better log output, I was talking yesterday, apparently it's possible to actually run Spark with a remote debugger on your cluster, right? So you can see things in a distributed fashion as they're happening. But I didn't have the luxury of that. And I had hundreds of tasks running simultaneously, logs spread out all over the place. And this really makes it hard to track down problems when they do happen. To get around this, I got in the habit of sort of peppering error messages with custom keywords. And what this meant is that then I could grep all the logs for instances. And this is sort of building on what Log4j naturally does with how you can break things out by debug, info, error, and so forth. But in that way, it really helps to narrow in on the problems and to track down what specifically is breaking. It makes it a lot easier to track actual state of the overall program. So how do we deal with all this? The first thing is really to tame the beast, the ungainly memory beast. The first thing to do, and the thing that's suggested time and time again, and so I'll mention it here, is to partition properly. And partitioning properly means that you have enough partitions and that you really understand your data, that you understand how big any particular piece of data is, how it's distributed such that you don't have skewed partitions where you might have one really big partition and a bunch of small ones such that executors will stall waiting for the big partition to complete before continuing, and to understand types. Because, as I mentioned before, that really helps you understand how much memory you're actually using. Secondly, using serialization will significantly decrease your memory usage and make you less likely to run into memory problems during shuffle and when you're moving data around. Secondly, memory cleanup. As I mentioned, I found that long-term jobs would consume memory indefinitely. And in a production environment, when I tried to use the mechanisms available to me, right, where I can tear down a Spark context and bring up a new one, even when it was possible to have multiple contexts running simultaneously, this caused other errors relating to yarn, related to HDFS. In short, it wasn't really tenable to do things the Spark way. Thankfully, we have another solution available to us, and that is to use yarn. So my approach was break things up into batches, and this proves useful later. So to the extent possible, when you can make any one job smaller, it definitely helps to do so because the memory load is less in that case, and you can have proper resource cleanup with yarn, and it makes it easier to be a better cluster citizen when you have a lot of small jobs instead of one mega job that hogs the cluster forever and doesn't let anybody else do anything. And yeah, so the result of this sort of optimization was that I could actually run this job for weeks at a time, which is how long it took to actually do all the compute that I had to do. The second thing is to really avoid shuffles. The reason for this is, as I mentioned, that things break. You'll get a great increase in how quickly things actually execute. You'll have increased stability. This is not a sort of definitive solution. There's obviously times when you can't avoid shuffle, right? Join's a useful operation. But in general, there are ways to write around using shuffle, and certain operations are much more efficient than other operations, like the typical example being how reduce by key is a much better implementation than doing a group by key followed by a reduce, because things are optimized under the hood. So how do you actually do this? There's a few ways. The one big way is if you actually define your own partitioning scheme. When you create an RDD, you can actually specify, or repartition RDD, you can actually specify how you want it to be partitioned. For example, you can basically tell Spark that you want all keys of a certain value based on some provided hash function to be aggregated together. And what this means is that when you, instead of having to go out through your cluster and reorganize all the data when it comes time to actually do a join, things are already co-located and you don't need to do a shuffle. The second thing that you can do is you can do what's called a map side join in Hadoop world, a broadcast join in Spark. But essentially, if you have a really big table and a really small table, such that the small table can fit into memory, you can avoid having to shuffle both tables, right? Shuffling the small table is fine, but shuffling the big table is expensive, by storing the small table in memory as a broadcast variable. And broadcast variables are a unique entity in Spark. They're essentially global variables that are visible to the entire cluster, but they're only ever serialized once, which means that they make fantastic lookup tables. Nominally, you can't really do a lookup efficiently in an RDD. It's an O of M operation where M is the length of your partition. But if you have a hash table stored in memory as a broadcast variable, then you have a constant time lookup, and it's a super useful thing that I use all the time. So that helps you avoid shuffles and helps you do efficient lookups, which definitely comes into play when you're trying to process a whole bunch of data efficiently. The problem is that actually using the driver is hard to sort of help you speed things along, because the driver is also a sort of constrained resource, particularly if you have a single client node that's shared by everyone that's trying to access the cluster. You've got limited memory to store any RDDs that you've aggregated on the cluster with collect. You've got metadata from shuffle, from the scheduler, and from other sort of under the hood stuff going on. You've got results accumulated in accumulators, which are another global variable that Spark provides for aggregating data. On top of this, actually getting things to the cluster can be, or to your driver node, can be problematic. When you want to aggregate all the data in one place, you have to serialize it and you have to transport it. If your Akka settings are misconfigured, you might end up trying to serialize a really big partition which exceeds the Akka buffer size. That'll throw a Akka error. Thankfully, that's a lot easier to track down than many of the other errors that one will see. But this is another instance of where it's important both to partition and to understand your data. So the point I'm just trying to drive home here is that all these things are interconnected. Lastly, because we have so much data, it's not necessarily an option to get all this data in one place on the driver. If we could do that, we wouldn't even be operating in a cluster in the first place. So basically, what I'm trying to say here is that use the tools available to you, right? Caching and aggregating the data such that you can have things stored in memory more efficiently than just using a cached RDD. This will make it possible to write more efficient jobs if you sort of expand your thinking from just what Spark allows you to do out of the box. The issue with doing this is cleanup and long-term stability. So we're going a little bit of a circle here because in doing this, that brought me to the cleanup issues, which I solved, but then moved on from there. So lastly, I'll talk about optimizations for actually improving efficiency. And first, obviously, caching is wonderful. When you can cache, you really should, but it's also a limited resource. You don't have infinite memory. In my experience, pretty much any time that I would reuse an RDD, either for a lookup table or because I want to do some, want to normalize a whole bunch of names based on some naming scheme, I would cache it. And you can evict things from the cache. You can do so manually. You can also this will happen automatically when things go out of scope. So as long as you're cognizant of what's in cache and how much memory you're assigning to it based on your configuration of Spark parameters, it really gets things cranking. Secondly, as I already mentioned, use broadcast variables liberally. You can configure how much memory is available to the driver, consequently how much memory is available to you to use for broadcast variables. But again, they let you do really quick lookups very efficiently. And lastly, this is a bit of a sort of custom thing that we ended up doing. But because for the final stage of computation in the collaborative filtering algorithm, we basically have to go through every user and every product and take the dot product of vectors associated with every user and every product, right? A whole bunch of distributed matrix math. This means that for every user, you have to do some distributed operation on the product RDD, and Spark doesn't let you do nested RDD operations, right? You can't do a map on an RDD and then do another map within that closure because it loses context. However, again, if you can store the first RDD or even a piece of that RDD in memory, you can iterate over that RDD and then operate over the second RDD. If you then parallelize this by having a thread pool and spinning up a whole bunch of threads to, for example, process a whole bunch of users in parallel, you can essentially dramatically increase the resource utilization of your cluster from what Spark would do out of the box. Because Spark isn't thinking about it in terms of, oh, you really have 2 nested RDDs here. It's just doing what you tell it to. It's got one big RDD, and although the operations on that RDD are quick, Spark can only do those one user at a time. The upshot of all this is that with all the optimizations that I've talked about to get things to be stable and to speed things along, coupled with this threading approach, I was able to get a over 75x speed up over the default implementation of the predict step in MLlib's collaborative filtering algorithm and make a problem that would have taken months to solve be done in a week and a half. So, thank you. Just one last thing. There's some really wonderful resources out there that talk about a lot of this stuff, but I wanted to consolidate it all in one place. There's a couple of really good blog posts from Sandy Rizza on the Cloudera blog about essentially the memory structure and how you can tune your Spark jobs to actually behave properly. So he goes into things in more depth than I do here. And the Spark tuning guide and programming guide are sort of hidden away on the documentation page for Spark, but those are great too, and definitely worth reading through. So, thank you.
Questions? Hi. Can you describe a situation where collect and broadcast is better than shuffle?
Sure. So the whole point is, right, say that I have 10 gigabytes of memory available to me, and I have a 2 gigabyte table, and I have a 400 gigabyte table that I need to do a join between. The use case specifically is, again, that I have to rename a whole bunch of merchants, for example, such that I can use the collaborative filtering algorithm, right? It needs ints, so I need to reassign IDs. The reason that doing a broadcast that's storing one of those RDDs in memory as a broadcast variable is useful is because there's actually a utility in Spark where you can iterate over each partition of an RDD in sequence. And part of the function is that you can say preserves partitioning equals true. And Spark understands that to basically mean that it doesn't need to reorganize data. It's already organized the way that you want it. And inside that closure, you can just reference this lookup table that's in memory. And you don't have to do a search, right? It's already there, already indexed by key. You can just do an ov1 lookup into your hash table, and things are super efficient. Instead of having to reorganize all the data, which is disk reads, network writes, et cetera. Does that make sense? Cool.
I have a question here.
Yes. Wait, sorry, I don't know what's happening. There you go.
Sorry,
buddy.
So when you broadcast, let's say, a collection, you have to materialize the whole collection. What if you have a fairly large data set, say 2 gigabytes? Will that cause GVM, GC tuning issues, GC issues, like stop
Yes.
the world? You will run into that.
You will potentially run into garbage collection issues. You will potentially run into memory issues. You will potentially run into ACA issues. The whole point is that you need to know that what the mechanisms are that are at play, such that you can work around those, right? That you can understand what it means when you get the ACA errors, that you can understand why you're running out of memory, because in reality, you think you have 8 gigabytes of memory available for cached RDDs, but you only have 4, right? Because of how memory is actually broken up under the hood. So you will run into issues, almost guaranteed, if you don't understand these configurations. If you do understand these configurations and these parameters and how they actually influence the sort of underlying operations, then it's possible to work around it, such that you can get the speed up from sort of doing things a little more hacky.
So, is it possible to save the broadcast variables off heap some way? Because I don't see any reason of keeping that stuff on heap. Right.
Possibly. I don't know.
Is there a question on this side?
So I had a question with respect to if with partitioning, and if you think one of your partitions are too large or something like that,
Mm-hmm.
what are kind of your best practices or suggestions in terms of tools that you would use to debug that or to find that out?
Sadly, there's not really a good answer to that question. The suggestion from the Cloudera folks is basically keep increasing the number of partitions by a factor of 2 or 3 until things work and until you stop getting performance gains. So it's kind of a heuristic. I do believe that they're working on making that process better.
Hi, great presentation. Can you speak to the value of the work you did here? Now, for example, was this an application that was impossible to build on another platform, or were you able to achieve an overall, X% improvement over a previous platform?
This was the cluster available to me. This was not a application built in place of another application. The 2 goals were pretty much build something that works and investigate Spark, right? Like learn Spark, learn it in depth, see if it will actually work. So that's why, I didn't, for example, look at paring down how much data we can actually, how much data we're actually processing, right? There's not an explicit need to process all the data. There's ways around that. But it was sort of an exercise of, can we actually do this? Is Spark the right tool for the job? When we need to process a crazy amount of data with Spark, will it work for that purpose? So it was really sort of a twofold goal there. Does that make sense? Cool.
Yeah. Hi. So you mentioned cryo, and just about every other thing I've read also mentions cryo. But in our experience, we've actually seen significant performance degradation using cryo. And digging into it, we see a lot of threads basically stuck in constructor access and using reflection.
Mm-hmm.
So I'm curious if you have any suggestions as to, or other caveats maybe that come with using cryo. Things like, does this require a default constructor that doesn't really gel that well with Scala a lot of times in the classes? So just any advice around that?
So with cryo, right, you sort of define the, essentially a scheme, right, for serializing things. I haven't personally run into these issues. I've also worked in Scala. My guess is that there could be something going on when you're actually defining sort of how to do the cryo translation, right, when you're creating your classes to feed into the cryo serializer. That's honestly the only thing I'd guess. I don't know anymore. I'm sorry.
Okay, thanks.